Hello, I'm Sharon Nolan with Eastman, and it's my pleasure to welcome you to Panel 3, Session 2, Technologies and Equipment Choices to Reduce Greenhouse Gas Emissions. I'd like to introduce our first speaker, Daniel Jordan. Daniel works for VEIC as a commercial and industrial energy consultant. He concentrates in manufacturing, wastewater, HVAC, and data analytics, and works directly with businesses in Vermont and New England to deliver energy savings and work towards decarbonization goals. Prior to joining VEIC, Daniel worked as a manufacturing engineer in northern New Hampshire, where he revitalized decades-old industrial processes. He holds a master's in mechanical engineering from Boston University and a Bachelor of Arts from the University of Georgia. Welcome, Daniel.
Thank you, Sharon. As Sharon mentioned, I work for VEIC. I'm here in Burlington, Vermont, and I work as a commercial and industrial energy consultant. And I'm excited to talk to everyone about industrial process cooling and specifically decarbonizing industrial process cooling. So what's interesting about this topic is that decarbonizing is not always the same as energy efficiency. They overlap a lot, but there is some difference. And similarly, cost savings is not the same as energy efficiency, is not the same as decarbonization. So one of the reasons that I wanted to take this on was to sort of look at differential savings across those different aspects of doing industrial process cooling projects. So here's an overview of what I'll be talking about today. So first off, how important is it, just to sort of motivate us, like why am I looking at this? Then I'm gonna show some photos and give some descriptions of different system types for industrial process cooling, specifically in Vermont, where I work on the Efficiency Vermont contract for VEIC. It's been a great resource for me to see a lot of different system types. So then I'm going to talk about some energy efficiency measures specific to industrial process cooling. And then we're going to get a little bit into more into the decarbonization side, specifically decarbonization as it relates to the electric grid source emissions. So what we're all talking about, sort of how to decarbonize through energy efficiency. There's a lot of sort of time of use impacts there and different choices that we can make. And then finally, I'll be looking at sort of a case study model to see sort of what happens when we apply some of these directly. So first off, how important is this? So this is a table from the EIA's Manufacturing Energy Consumption Survey. What I'm taking from this is that 8.6% of all electricity used in manufacturing goes towards industrial process cooling. So there's a lot of different ways to cool a process, but when we put them all together, you've got 8.6% of all electricity in the manufacturing sector that goes towards this. So that's one reason that it's important. Secondly, this is sort of approaching decarbonization, not necessarily from an energy efficiency point of view, but this is a photograph of the inside of an electric panel of a 40-ton chiller, where there's notes there that have been made by a technician that the system was charged with 144 pounds of R404A, which is a refrigerant. And all chillers, and we'll get into this, but chillers use the vapor compression refrigeration cycle to cool. That's one of the ways you can do it. It happens to be one of the more energy intensive ways to provide mechanical cooling. But refrigerants as we use them today have very high GWPs, very high global warming potentials. So in this case, 1 pound of R404A is equivalent to 3,900 pounds of carbon dioxide as far as global warming potential. And refrigerants exist at atmospheric temperature and pressure as gases. Essentially what I'm drawing attention to here is the fact that this system contains enough refrigerant to have the same GHG impact as running it fully loaded for 13,500 hours if all of that refrigerant were to leak out. So this is just something to keep in mind as we think about let's call it sort of mitigating GHG risks. We have to realize this is a GHG liability, and I'll talk a little bit more into how that relates to specific technologies. So yeah, that one always kind of takes me back a little bit. So next, I'm going to give an overview of different system types in Vermont. I'm just going to show photos of 3 different systems so we can kind of know what these things look like and what we're talking about, and I'll talk about energy efficiency measures with some of these systems as well. So this is a bottling line. You can see the bottles in there. So this is at a food processing facility. The bottles are being filled, and then they're being cooled quickly. You need high capacity cooling to cool the bottles to spec. So there's what we'll call a process water or process fluid that's contacting the bottles directly, and flowing over them and drawing heat from them. So this is that same system. So I'm assuming folks can see my mouse. Great. So the process water runs up through these stainless steel pipes, through the heat exchanger. It loops constantly. The heat exchanger has these copper pipes coming in are a separate loop. So this is what we'll call a chilled water loop, and this separate loop runs outside. It's a mixture of an antifreeze like glycol and water, so that when it does run outside, it won't freeze. But you can't, or they don't want to expose the product to that. So that's why there's a heat exchanger, and the fluids are only exchanging heat. There's no sort of direct interchange. So the next photo, we're going to follow these copper lines that are in the white insulation going outdoors. So this is the outdoor side of that cooling system. This is a 30-ton cooling system. You can see the white insulation outside has metal jacketing to keep it protected. I think it looks really great. This system was just installed at the time I was taking this photo. So you're looking at 2 different pieces of equipment. On the left is a dry cooler. It's basically just 3 fans. The dry cooler is activated whenever the outdoor air temperature drops below 40 degrees Fahrenheit, because that's when the air is cool enough that we can just provide those 30 tons of cooling by blowing cold air over heat exchangers with the chilled water loop inside. And so that's a pretty efficient way to do it because it's just fan energy. So these red valves are thermostatic valves that control whether or not the dry cooler is running. On hot days in the summertime, instead we'll use the chiller, which is this piece of equipment on the right. It also has fans. You can't really see them, but they're in that sort of top portion. And I'm going to step inside the fence here. So here's the chiller again. So again, there are, I guess, probably 3 fans up there. But the big difference between a chiller and a dry cooler is that, I mentioned this earlier, but a chiller uses the vapor compression refrigeration cycle, just like a refrigerator. So these 2 little black units that are, they look sort of like fire hydrants to me. They are compressors, and they are responsible for manipulating the pressure and temperature of the refrigerant to dump heat. So this is an easy way to identify whether you're looking at a chiller or a cooler, is look for the compressors. And similarly, if you see a lot of high surface area, kind of small copper piping of different diameters, that's probably refrigerant running in there. So this is a sort of a third loop is the refrigerant loop, as the compressors compress the refrigerant and then dump it into the condensing unit. So the sort of big thing here for energy efficiency, these 2 compressors use something like 10 times the amount of energy as the fans, even though they're smaller. And fans are big and loud and they get a lot of attention. But if we're going to talk about energy efficiency, we should really focus on the compressors. And I'll talk a little bit more about that in a second. So here's an overview of 3 different system types to kind of help frame what we've been looking at. So a packaged outdoor unit, this is exactly like the one we just walked through. So we were just looking at the refrigeration cycle outside with the compressors. That's exchanging heat with a separate chilled water loop, which is in turn exchanging heat with a separate process loop, which is that water that's falling over the bottles and shedding heat. So that's a packaged outdoor unit. But at the time that this customer was that I was working with them, they were evaluating a couple different ways of doing this. They got a few different proposals. A packaged outdoor unit is one way to provide 30 tons of cooling to their process. They could have also done a split system, which would have been a little bit simple. Well, it would have involved fewer loops. So you've got the process cooling. With a split system, the high side of the refrigeration cycle would be what's piped through the wall outdoors. So the condensing unit and the compressors would be outside outdoors. And then what goes through the wall would be the refrigeration cycle itself. So instead of those metal jacketed, chilled water pipes going through, there'd probably be smaller diameter, rigid copper pipes going through. And you would have to field crimp the refrigeration lines. And then finally, you have a packaged indoor system where you're just dumping the heat indoors, but it's really easy to install. A manufacturing engineer could probably install it themselves. You just get the chiller, put it right next to the process, but there are obvious drawbacks to dumping 30 tons of heat inside your facility. So one thing I want to point out from a perspective of the sort of GHG mitigation using refrigerant, like I mentioned in the beginning, field crimped refrigeration, it's been found in studies of heat pumps that field crimped refrigeration lines are more liable to leak than packaged refrigeration lines. So packaged indoor units, packaged outdoor units have lower GHG liability. A split system, which would require field crimping refrigeration lines and running those connections by a technician in the field versus at the OEM, that would be sort of more liable to leak. And that's not to say that you can't have it installed perfectly, but there are lots of additional measures you need to do, vacuum testing, in order to make sure that that those refrigeration lines are perfect. So some quick terminology. Again, a chiller uses the refrigeration cycle, and a cooler just uses fans and pumps, does not use refrigerant. So there's dry coolers and cooling towers. Many of you, especially if you're in, not in a cold climate, might be more familiar with cooling towers. In Vermont, we see a lot of dry coolers, and so my paper doesn't really touch on cooling towers, for example. This is a second system. What you're looking at here is two outdoor packaged chillers, and the reason they're packaged chillers and not the outdoor side of a split system, one giveaway is that the piping here is flexible, and if that were refrigerant piping, it would not be flexible. It would be rigid, because it would need to be rigid copper piping to deal with the pressures that the refrigerant cycle runs at. But the other giveaways, it says like cool chilled water on those pipes if you look closely enough. This is the final system that I'll show you. This is an outdoor condensing unit. So this is the outdoor side of a split system. This one is about 40 tons. So the refrigerant cycle is running through the wall to this system. It looks a lot like an outdoor package system. Here's another shot. So these two pipes there's refrigerant running in there, and this is sort of the nameplate of this one. So again, this has two compressors that run at 40 amps, and then it has four 2-horsepower fans. So this kind of shows that, again, the compressors are using a lot more energy than the fans. Stepping indoors, the refrigerant is running through these copper pipes, and then it's expanding and then running into the heat exchanger, where the refrigerant is evaporating and pulling heat from the process water that directly touches the process. So we'll step inside and see what's happening inside this heat exchanger. This is called a falling film heat exchanger, and I never even heard of this before I saw this one. It's really wild. So on the left, it was really iced up because they tried to increase their capacity by bypassing their condenser fan cycling controls, and that caused the process water to freeze up, which actually hurt the capacity of the system. And so on the right, it's running as specified. So inside these big plates that sort of look like pillows, the refrigerant is evaporating and pulling heat from the process water that's trickling down, and then kind of runs back to process at a nice like 32.0001 degrees Fahrenheit. So it's not freezing. I'll just touch on this briefly. On the y-axis, cost per ton of different systems, and then on the x-axis is the integrated energy efficiency ratio of those systems, which is a function of where it is too. That's why it's integrated over the season. And it's what you would expect, right? The more efficient systems cost more. This one, the split system, sort of evades the line a little bit, because there's you don't have to add a dry cooler here. But the reason I have it red is because of the GHG liability that I mentioned earlier. So I've got maybe 5 or 6 minutes. I'm going to move on. I'd be happy to answer questions about incremental costs. But the efficiency premise behind a lot of the industrial process cooling that I see in Vermont is that in cold climates, systems with outdoor units can use cool air to boost efficiency. So how does that happen more specifically? Well, remember the compressor, the big energy user. We're going to look at specifically what's going on in a compressor where it can use outdoor air to boost its efficiency. So here's a data sheet from a compressor. So when an equipment manufacturer is building a chiller, they're going to specify some compressor to go into the chiller and power the refrigeration. This is a data sheet from the chiller. There's a lot going on here, but on sort of the y-axis of this matrix, you've got the saturated condensing temperature, which is the high side of the refrigerant. The premise behind what we call low condensing or floating head pressure is reducing the saturated condensing temperature coming out of the compressor, which boosts efficiency, which is going to be the E line here, which stands for EER. So that goes up, but then capacity goes up as well. So a lot of times chillers come from the manufacturer with a fixed head pressure specified that they see as safe, like 110 degrees, 120 degrees. As long as it's always going to be hotter than the hottest day outside, that compressor, because that's what they're concerned with, is the compressor, meeting capacity. With controls like floating head pressure controls, we can drop the head pressure of the system, drop the saturated condensing temperature down to see efficiency go up and to see capacity go up on days when it's not so hot outside that you need to run 110 or 120. Someone asked yesterday, well, what happens on super hot days? Well, what happens on super hot days is, in order to maintain the delta T between the saturated condensing temperature and outdoor air temperature, the condensing temperature is going to go up, and that's going to conversely or inversely, I guess, drop EER and drop capacity. So that's what's going on a really hot day when your system, might not be able to keep up, is that, this E number at 130 is 12.1, but then when it goes up to 140, the E is 9.9. So that's the efficiency going down, but we should look at C, which is the capacity. The capacity is going from 422,000 BTUs per hour, dropping down to 388,000 BTUs per hour. But that has more to do with the sizing of your system. Even big systems can still have floating head pressure and can modulate this saturated condensing temperature to maximize efficiency when the outdoor air is cool. So I didn't think of this. There's actually a previous ACEEE paper that I cite in my paper that looks at floating head pressure controls in refrigeration, but it is a proven technology in refrigeration. So it's the same technology that we use in high efficiency condensing units. So Efficiency Vermont is the contract that VEIC operates for the Vermont Department of Public Service. And with Efficiency Vermont, the sort of floating head pressure of high efficiency condensing units has gone midstream. And so now folks can get point of purchase rebates. But I want to bring this to an industrial process, or I would like to see more of it in industrial process. So there are some challenges associated with doing that. One is that process cooling might be too warm for low condensing. We're looking at set points of 50 or 60 degrees versus refrigeration where it's more like 0 degrees for freezers, or up to like 30 or 40 degrees for refrigerators. Another challenge is not all industrial process compressor types allow floating head pressure adjustments. So ask about that if you're specifying one for your system. And a third challenge I'm finding is that HVAC technicians don't always know about this. Refrigeration technicians are more likely to know about this, and controls ones are as well. So again, I would like to bridge the gap from refrigeration where it's proven out to industrial process. So I'm going to just kind of quickly talk about time of use carbon impacts with industrial process chilling. So this is a really interesting graph. This is over calendar year 2019. What is the electric grid doing as far as carbon emissions? So day of year on x-axis from January 1st on the left to December 31st on the right, and then hour of the day goes on the y-axis as we move down. So summer daytime is this really bright part in the middle where the carbon intensity is close to 1 pound of CO2 per kilowatt hour. But then, on the shoulder seasons in the middle of the night, if you're in New England and buying from the ISO New England marketplace, the carbon intensity of your electricity is less than half of that, 0.4 pounds per kilowatt hour. So, and we also know that industrial process cooling with floating head pressure and dry coolers runs more efficiently during those hours as well. So you would see a compounding effect by avoiding these sort of coincident peaks by, for example, moving this system from third shift to first shift. So I don't have too much time left, but you're welcome to take a look at my paper where I do a full analysis of what happens if, for example, this plant decided to run this 30-ton cooling process on third shift instead of first shift. Here are some kind of quick graphs that show that. This is what happens on the 20th of June, 2020. This is what happens on the 10th of October, 2020. You can see like this precipitous drop here is the outdoor air temperature goes below 40, so the dry coolers kick on and the chiller can shut off. So if they were to run it on third shift, the process would only use 73 kilowatt hours, but if they run it on first shift, it would use 142 kilowatt hours because it was warmer on first shift. But that's just energy savings. The electric grid is, in both cases is this lower graph, and you can see the carbon intensity of the electric grid on third shift was 0.62, and then on first shift it was closer to 0.7. So that's sort of a small change, but some days, like in the summer, it'll swing from like 0.6 up to 0.8. So when we look at, these are just savings curves. So on that summer day, 20th of June, here's the energy savings in the blue line, but the carbon savings, dip deeper than that because we're talking about not only a system running more efficiently, but also the electricity being lower carbon. So here's, just briefly, here's a table. You can find it in my paper that shows sort of differential cost savings, carbon savings, and energy savings because they are kind of different. So my conclusions here, just to, in cold climates, ask about low head pressure. One thing I want to point out is you don't have to move it from first shift to third shift. You could also investigate thermal storage, and you could downsize your system, have a system that's half the capacity, make chilled water at nighttime, store it in a tank, and then run it during first shift. And then your smaller system would then be supplying like sort of trim chilling, and your whole system would be smaller. So you'd be avoiding peak demand charges doing that. And save even more costs. So I'm going to go ahead and wrap up now. You can please reach out to me with any questions. Thanks everyone for attending today. I'm excited to see the next ones.
Thank you, Daniel. That was a great presentation. Next up, we have Vansh Vyas. He is a PhD student in industrial engineering at Louisiana State University in Baton Rouge, Louisiana. He is working at the Industrial Assessment Center at LSU to help small and medium-sized manufacturers reduce their energy use and carbon footprint. His area of research is energy simulation and optimization. So welcome, Vosh. We're looking forward to hearing your talk.
Thank you, Sharon. Hi, everybody. I'm Vansh, and today I'll be presenting my study on simulating a manufacturing system, including an air compressor for reducing energy costs. So just a quick review on the research motivation behind this project. So usually compressed air is one of the most commonly used system in any manufacturing industry, and it accounts for about 5 to 20% of facilities' annual electricity consumption. And in US, it accounts for almost 10% of the total electricity consumption. So huge potential savings, energy savings can be achieved just by making the compressed air system more efficient and improving the system. It can account for almost 20 to 50% of the energy saving just by making improvements. These are a few of the notations that I'll be using in my presentation, and you can also find these in my paper. A brief introduction. So usually manufacturers' electricity cost consists of two charges. One is the energy charge, which depends on the total kilowatt hour consumption, and one is the demand charge, which depends on your peak kilowatt. There are various energy simulation techniques that have been applied to material removing operations, such as milling and turning, to estimate the energy cost of machining processes. although machining energy simulation studies are available, but they have not been thoroughly performed to see the effects of machining parameters and compressor system parameters on energy performance, including energy consumption and energy costs. So what is a compressor system? So basically a compressor system is a system to provide compressed air for various production processes such as dry machining. It might be cleaning, it might be compressed air for various pneumatic tools. And as you can see on the right, there are two main parts of the compressor system. One is the air supply side, which comprises of the air compressor related components such as air inlet filter, your compressor unit, dryer, air receiver, etc. And the other is the air demand side, which is the consumption side of the compressed air, which includes your machining tools and so on. There are three most commonly used compressed air system. One is rotary screw, one is reciprocating, and one is centrifugal. I will be using rotary screw compressor for my research purposes since it is the most commonly used system. To maintain the supply and demand of the compressor, usually the compressor systems are equipped with six control modes, as you can see on the screen. And out of those six control modes, I'll be choosing a start-stop control mode for with the rotary screw air compressor with the start-stop control mode for our research purposes. So what is a start-stop control mode? So usually a start-stop control mode has two modes. One is a start and one is a stop mode, which is very evident from its name. During the start mode of the air compressor supplies compressor till a specific discharge pressure is met on the air compressor. And the power consumed by the air compressor during that start mode is estimated as 10% above the rated horsepower of the air compressor. Although during the stop mode, there is no supply of compressed air to the system, and the the, the driving motor of the air compressor is turned off during the stop mode. Usually, since there is no supply of compressed air during the stop mode, this type of system is equipped with air receiver to have a constant pressure supply during the stop mode of the air compressor. As you can see on the right, there's this sample power profile of the air compressor working on a start-stop mode. And the average power required by the compressor can be calculated by the formula given on the right. So we are using fundamental equation governing the dynamics of air receiver to estimate the duration of start mode and stop mode for the air compressor, as you can see on this slide. And for the start mode, we will the time duration for the start mode is the time to fill the air receiver till the air receiver pressure equals the discharge pressure. Well, for the time duration of stop mode, it is the time taken for the pressure inside the air receiver to drop till the pressure at which the air compressor starts again. And we will be using these formula to estimate the time durations for both the modes. A quick background of the research. So there have been studies available in the compressor system area related to the studies in energy savings and what are the various factors that impact the energy savings of the compressor system. So few of the modifications that impact the energy consumption of the CS can be reduction in discharge pressure, usage of high efficiency motors, matching supply with demand, and so on. Also, the researchers have developed method to estimate the operating efficiency of a compressor system for various control modes by studying their power profiles. And additionally, compressor system power profiles have been used to estimate the energy savings based on the collected power data using the simulation software. When it comes to the material removing process, processing rate has been identified as the main component of energy model, and there are various studies that have been developed to study the energy consumption of material removing process, such as milling and turning, using various simulation studies such as discrete event simulation and numerical simulation. So, what usually to estimate the power consumption of a process, you need a power data, and it is hard to estimate the power data without disrupting a production process. Um, So this is one of the concerns, and that is why we are conducting such kind of research, so we can use simulation techniques to estimate the power consumption of a process, specifically my air compressed system integrated with the machining energy consumption. Since they both have not been studied comprehensively, we are proposing a pressure discretized simulation model that integrates machines and compressor system to see how much impact each machining or compressor parameter has on three energy performances: energy consumption, peak kilowatt, and energy cost at factory level. So our main goal is to reduce the energy cost of a production system by controlling the parameters of the compressor and production machines. And I've already mentioned we are developing a pressure discretized energy simulation model uh, uh, to achieve our goals. The contribution from this paper uh, can be used by academic researchers and manufacturers to study the power demand and to optimize their production schedule. So for the power estimation of the CS, we have available some available formulas as mentioned on the screen. For the start mode, we are using power as 10% above the rated horsepower. For the stop mode, air compressor consumes zero power, and based on these two equations, we are calculating average power as shown on the screen, and further we'll be calculating total power consumption of the CES. And to estimate the power profile, we need four parameters as shown, which is the time duration for start mode, stop mode, power required during the start mode, and stop mode. As you can see on the figure on the right, and I have highlighted, these four parameters will define the power profile of the air compressor. Since the pressure change and air demand are continuous, it is hard to generate the power profile just by using the current equations. So, in order to achieve that, we are discretizing the pressure range into equal fragments of zero point 0.5 psig, and we are developing an algorithm to change the pressure inside the air receiver by zero point 0.5 psig for both the start and stop mode of the compressor system. And on the below, you can see an example of a power profile that we want to achieve. So, as I mentioned in my previous slide, we the pressure described algorithm is based on the fixed change in pressure for the start-stop mode, and we are defining the time duration for those pressure change to occur for the start and stop mode. During the start mode, the pressure will be increasing. Uh, Therefore, we are defining the time to increase the pressure by zero point 0.5 psig for the stop mode, and for the stop mode, we are defining the time to decrease the pressure by zero point 0.5 psig. Uh, in the air receiver. And here in the equations on the left for the time durations, the parameters V, S, and Ci are fixed, which is the air receiver volume, the supply rate from the air compressor to the air receiver, and the air demand. This is a summary of the methodology that we are using. So our model is based on two of the modes of the air compressor. So we are defining the start and stop mode in the air compressor based on the pressure settings, and and from there we are defining the time duration for both the modes to increase or decrease the pressure depending on the mode of the air compressor. For the machine level power estimation, we already have a basic of power equation, which is shown on the screen. And here B2 is this idle energy consumption of the machine, B1 is the specific energy consumption, A is the material removal amount, and T is the processing time. And for our research purposes, we are considering turning machines that process brass parts. And as shown on the screen, the turning machine parameters for the materials is adopted from a reference, and we are using the parameters for the brass based on this table. For the factory level power estimation, we are creating a simulation designed for estimating the energy at the factory level. We are using two softwares, which is Simio for discrete event simulation and MATLAB for numerical simulation for our purpose. And we are defining the production layout and all the related parameters in Simio. And we are generating timestamps for the machines and compress there. And based on those timestamps, we are generating power profile and defining the power for particular time when the CS works on the start mode and stop mode, and we are integrating the power of the compressor system and the machine together to create a time series power for the facility level. A brief summary of our methodology is shown on this slide. So, coming to our simulation model setup, we are using four turning machines as shown in the figure with four different part sources which processes brass parts and a 7.5 horsepower rotary screw air compressor with start sub control providing compressor to all these machines. The compressor is rated at 21 CFM at 155 psig with motor efficiency of 91%, and we'll be using this data for our calculation purposes. The machining process time is normally distributed with CV is zero point 0.2, and as A, B2, and B1 are chosen from the turning machine parameters as shown on the previous slides. And we are choosing a simulation time of 18,600 minutes and 20 simulation cases, 4 simulation sets with 5 cases each for our analysis purposes. So the first set is our baseline set of the experiments, and the case C11 is our baseline case for our baseline scenario, and it is based on the realistic CS parameters. We are using 5 CS parameters, which is air receiver size, LT is the amount total intensity of air leakages, P stop and P start the pressure set points for the start and stop mode, and CM is the machine level air consumption. And we are using the 15-minute moving average peak kilowatt and total kilowatt hour consumption as our machine as our energy performance measure, and we are using the existing electricity rate from the 4 different states for our energy calculation cost calculation purposes. We observe, based on a simulation, we observe that the size of the air receiver does not have much impact on the energy performances, which we can see from C12. Coming from C11 to C13, we change the total intensity of air leakages, and we observe that the total kilowatt hour consumption, the peak kilowatt and energy cost is increased. In case C14, when we increase the pressure set point, discharge pressure, it also increases the total kilowatt hour consumption and energy cost. And for case C15, the reduction in machine level air demand also reduces the total kilowatt hour consumption, energy cost, and peak kilowatt. In set 2, we wanted to see the effect of variability in machine processing time on the energy cost. So we use an exponentially distributed machining process time. For this case, all the rest of the parameters are similar, just the machine processing time has been changed. Since the material removal rate is likely to be higher than set 1 because of the higher variability, we see that the peak kilowatt is higher for set 1, and thus the energy costs will be higher. So we can see a clear increase in demand for the exponentially distributed processing time. For simulation set 3, we decreased the machine level air demand by 25%, keeping all the parameters same as these as set 1. And the air demand decreases, the CS would have to work less as compared to set 1. Therefore, the average power consumed by the air compressor would decrease. Eventually, the total kilowatt hour consumption of the CS and factory, the peak kilowatt and energy cost would be lower as compared to set 1. For the simulation results of set 4, we are decreasing the pressure set points by 10 psig from set 1, and since the pressure set points are decreased, that is, the discharge pressure is also decreased, so the CS would work less duration of time on start mode, since the supply rate of from the air compressor to air receiver would be higher for a lower pressure setting. Therefore, the average power consumed by the compressor is lower. Eventually, the total kilowatt hour and energy costs are lower. As you can see from the figure on the right, it's a pressure profile for case C11 and C41, for example. And we can see that for C11, the time duration to reach discharge pressure of 130 30 psig is more than the time taken for the air compressor to reach the discharge pressure of 120 psig. So we can clearly see a difference over there. Also, looking at the power profile as an example for C11 and C41, we can clearly see that the time duration for the start mode of the compressor system, which is the upper limit of the power profile, is longer than that of C41, which clearly shows that the energy consumption for C11 would be higher than the case C41. So clearly, discharge pressure is an important factor for reducing energy costs. Let's come to the future scope of features and conclusions. So we found that the significant factors that affect the energy performances and energy costs are magnitude of compressed air leakages, discharge pressure, machine level compressed air consumption, variability of machine processing time. Although size of the air receiver was found to have limited impact on peak kilowatt energy consumption, so there are a variety of ways that manufacturers can reduce their energy costs, such as if they reduce their compressor leakages, which can be achieved by preventative leak maintenance program if they have one. Keeping a lower discharge pressure, reducing a discharge pressure just by a few months can result in huge energy savings. And reduction in variability of machine process time also has the potential to reduce the energy cost for the manufacturers. Overall, the simulation model can help manufacturers in reducing their energy costs and carbon footprint by choosing optimal parameters for the CAS and machines before applying it to the real system. Although in this model, we did not consider pressure drop across the distribution system, and we expect to address this in future study. And this is all from me, and thank you so much for listening. Please feel free to contact me if you have any questions. Thank you.
Thank you, Vash. We certainly enjoyed hearing about some very interesting work that you're doing. Uh, our third presentation, we have two presenters. I'd like to introduce them. The first is Joel Zalin, and Dr. Zalin has over 11 years of experience in the energy efficiency industry, including broad experience in project management, engineering analysis, and research. He is a senior member of Cadmus's commercial and industrial practice. He leads several impact evaluations covering the full range of non-residential applications focused on delivering actionable insights for a variety of clients. One of the things I found most interesting in his bio is that he co-authored the U.S. Department of Energy Uniform Methods Project Compressed Air Evaluation Protocols in 2020. He's worked on over 150 energy efficiency and process improvement projects at commercial and industrial facilities, resulting in savings of over $30 million a year. Joining him will be Evan Talon. He has 4 years experience in industrial and residential energy efficiency. He supports the Cadmus Energy Services team in industrial and commercial energy efficiency projects. He has experience in industrial M&V, strategic energy management, and on-site and virtual inspection. He worked at the Industrial Assessment Center at Oregon State while obtaining his degree in mechanical engineering. We heard that our previous presenter also worked at one of the industrial assessment centers. That's really a great program at the DOE if you're not familiar with it. So while he was there, he spent 2 years performing industrial energy efficiency audits of major manufacturing companies. He collected data on industrial systems and performed engineering analysis. After receiving his MBA from Seattle University, he managed a big data analytics team to perform measurement and verification of residential utility energy efficiency programs for RES Intel. So welcome to our next two speakers.
Okay, good afternoon. Thank you, Sharon, for the introduction. Good afternoon, everyone. Hope you're all doing well. Today, as Sharon mentioned, I will be presenting with my colleague, Evan Talon. Evan and I both work on the commercial industrial engineering team at Cadmus. When the ACEEE conference theme came out for decarbonizing industry, we started to discuss ways that we can potentially contribute to the conference and felt it would be useful to highlight the opportunity of waste heat recovery in industrial facilities and dive into some of the larger waste heat recovery projects we came across over the past year. So let's go ahead and dive in. Industrial facilities are responsible for about 23% of total greenhouse gas emissions in the United States, which totals over 1,500 million metric tons of CO2 equivalent. The DOE estimates that between 20% and 50% of industrial energy input is wasted as heat, which is significant. And an estimated 1.4 quadrillion BTUs of waste heat could economically be recovered, which would translate to 9 to 10% of total industrial energy use in the US. And as we all know, to meet the greenhouse gas reduction goals, there needs to be long-term strategies for significant reductions in the US greenhouse gas emissions by 2030 and potentially net zero by 2050, including carbon emissions. Per ACEEE, in some recent publications, energy efficiency is one of the main drivers for industrial decarbonization and can get us halfway there. So it is critical to focus on this. And on the shorter term, also per ACEEE, there are estimates that energy efficiency can cut industrial emissions by 15% today through relatively simple and inexpensive modifications to industrial buildings, equipment, and operations. So for this paper that we wrote, we are going to cover 12 of the largest waste heat recovery projects that we came across this year. These projects totaled about 10 million therms in savings per year, offsetting over 52,000 metric tons of CO2 per year. And we're also going to cover some barriers and opportunities. These were based off of discussions with customers, energy advisors, implementers, and also subject matter experts from within Cadmus. And then just to give an idea of the potential of heat recovery in the US, based on the systems that you see in the table, there is energy lost between 3% on the energy distribution side, all the way up to 80% on the motor system side. As Vanch covered on his compressed air presentation, compressed air is notorious for losing energy to heat, and it's estimated, somewhere between 70 and 85%. So there is tremendous opportunity, and waste heat recovery can potentially offset 9 to 10% of energy use in industrial facilities. So it is a significant opportunity here. So I'm going to pass this on to Evan, who will go over the types of waste heat and some more details on the projects.
Yep, thank you, Joel. So when we look at types of waste heat, we typically can categorize them in a few different ways. One of those ways is by temperature. So I have a few examples here ranging from, below 250 degrees Fahrenheit, temperature up to, over 1800 degrees. And different types of technologies can be used at these different temperature ranges. So there is low temperature power generation. There's higher heat with the RTOs, with recovering exhaust gas. But typically these larger systems are produced for manufacturers with application-specific designs that meet process needs. So we're going to go over some of the technologies that we looked at in this evaluation in the next slide. So here we have 4 categories of waste heat recovery technologies, and we have them roughly graphed by potential as we see, in industry and ease of implementation. So the first one being heat exchangers. This is used to recover waste heat, waste streams, and redirect process to processes that require additional thermal load. So you can think of preheating combustion air as an example we have there. Similar to heat exchangers, there's load preheating, and this is when waste heat is used to preheat a load going directly into a system that needs additional thermal energy. So boiler economizers are a great example of that. Load preheating does have a few risks in direct fired systems, so product quality, emissions, and complexity are all things people need to take into consideration when implementing these. And then there's power generation. And this typically will be seen at facilities that have a need for low pressure steam. They're able to run it through a generator, and then the high pressure steam becomes low pressure after that, after taking off some of the energy for generating electricity. Newer technologies have been able to directly generate electricity from heat. This is called thermoelectric generation. Although it hasn't seen widespread adoption yet, it's still in sort of a research phase. Lastly, we have low temperature heat recovery, which is a big topic of research and continued implementation. hopefully reaching the industrial sector and widespread in the future. We have sort of a cloud there to show that there's a possibility for much more potential in the future as technologies catch up. There are a few challenges with low temperature heat recovery that aren't exclusive just to that, but these ones are very specific for low temperature, and that's corrosion, size constraints, and then limited use for low temperature heat in a facility. Next, we'll look at the benefits of waste heat recovery. So a lot of them are pretty obvious. If you use less energy, you're paying less to the utility company. And if there's also reduction to equipment sizes. So if you're doing something more efficiently, you can, reduce the capacity necessary to purchase to do that same process task. Next, we have operating and maintenance costs. So because they reduce energy costs and also typically reducing capital costs with reduction in equipment sizes, you're reducing operating costs. Lastly, there's the reduction in pollution. So waste heat recovery projects reduce GHG emissions associated with industrial processes. And facilities are definitely catching on to not only the utility side and the cost reduction, but also the potential future costs that may be associated with reducing GHGs. We talked to one facility project engineer, and he expressed to us that they're looking at reducing GHGs just because they are expecting incentive structures to change, as well as carbon taxing to start playing a role in their operating costs. Next, we'll look at the actual projects that we selected. So these are all large waste heat projects. There's 12 of them, ranging from 250,000 to 1.5 million therms. The industries we saw were forest products, chemicals, metals, water treatment, and food products. Technologies were heat exchangers, regenerative thermal oxidizers, water recirculation systems, and plenty more. 3 waste streams is what we broke them up into. So there's 3 groups of 4 projects broken up into exhaust air, hot water, and steam. And the primary fuel for all of these projects was natural gas. So here's our large table of all the projects that were selected for this paper. And I'll go through certain examples of each 3 of the streams. But here you can see we had an average price over all 50 states for price per MMBTU of gas. You can see the paybacks there if you really want to take a look. It is a dense table, so I will get into the examples now. So the first example we have is an exhaust air example. So the facility was looking at replacing, well, not replacing, they were looking at installing either a DFTO or an RTO. They're both thermal oxidizers. One is direct fired, one is regenerative. Typically, what facility managers are deciding between is meeting environmental regulations and then cost. So DFTOs and RTOs both will meet environmental regulations typically. DFTOs are slightly more effective at destroying VOCs that get released into the atmosphere. However, RTOs are much more energy efficient. So when talking about costs and reducing all the utility costs and reduced capital costs, this is an instance where reduced utility costs over the lifetime make up for that reduction or the lower capital costs of the DFTO. This project resulted in significant energy savings, so over 1.25 million therms, and then it had a cost of less than a cent per therm over the effective useful life of the RTO. Next, we'll look at a steam example. So this example of this project was eliminating direct steam injection and they were directly injecting steam into product because it was a food production facility, or food products production. So what happens is you inject direct steam and then it condenses into the product, and that's water that you'll have to boil off later on. So you have to essentially boil that water twice. This project was actually originally identified by a facility engineer, and they're very keen on reducing the amount of waste heat that's just left to escape to the atmosphere at this facility because it's money out of their pocket. And these projects, these big ones that stop production, are under extreme scrutiny for a quick payback at this facility. It's a really large facility. It's a really large player in their industry. So a quick payback is definitely something that they require, needs to make up for the reduction in throughput. And this resulted in a cost of around 2 cents per therm saved over the lifetime, which is, again, significant. Lastly, we'll look at the hot water example. So this was a paper mill that was actually able to chemically treat their water after producing, some sort of part of the paper production process. And they were actually able to recover pretty much all of their water that would typically be lost to the drain. With that, they're recovering the heat that they already heated up that water towards. So water has a high heat capacity, as we all know, and it's abundant in these industries like pulp and paper. So that's why we saw a significantly low cost of, around less than a cent per therm again over the lifetime of this water recirculation system. Next, we'll talk about some assumptions and uncertainties with the projects that we picked and the analysis we did. So these were all hand-picked projects. There were 12 of them, and we picked them because they were the largest in across the 3 evaluations that we did. And maintenance and upkeep of systems, so the cost of those was not considered for the cost of these, of operating these pieces of equipment. The estimated useful life was either estimated from program data or taken from TRMs. And then lastly, electrical penalties, either positive or negative, actually were not considered. So maybe it's a wash, but we focused strictly on natural gas projects with no other savings in terms of electrical. All right, so the analysis and benchmarking. So essentially some of the results we can look at. As we can see, in terms of payback period and cost per lifetime therm, hot water significantly outperformed both steam and exhaust air. Things are changing, but we've typically seen that a 2 to 3 year payback or less is an acceptable project at most large industrial facilities. And that's different depending in each industry and certain companies, but generally that's what we see. All these projects, except for exhaust air, were under 2 years. Hot water just being extremely quick with a 0.14 year payback, so a couple months. Next, we have a cost per lifetime therm, right? So hot water being almost half a cent for cost per lifetime therm is definitely a low cost for implementing such large projects. And we did benchmark these numbers against all the program data that we had. So any natural gas project, we looked at the cost of implementation and then the savings over the lifetime of the projects. And those came out to about around 15 cents on average. And as you can see, that's not even on the graph of cost per lifetime therm. So waste heat projects, I think, are proving to be, at least these 12 have proved to be very cost effective in terms of cost per lifetime therm. Next, this is sort of the results and the reasoning why we think hot water was the outperformer. So all 4 projects in the hot water category were pulp and paper industry, and that relies heavy on hot water. It's abundant across that industry. And then hot water can also be directly added into process, so there's minimal losses. You think of steam or exhaust air, it's pretty easy for that to escape or heat to be lost to the environment. Project in the sample were system repairs and water recirculation, so not just repairing the system, but also with the recirculation that was installing new equipment and chemically treating. So minimal cost too if they already have that equipment on site and they just need to reroute. And then I'll pass it over to Joel, who's going to talk more about some of the barriers, some of the insights we got from facility managers and facility engineers, and take us through the conclusions.
Yeah, thank you, Evan. As Evan mentioned, I'm going to cover in the next 2 slides some barriers to waste heat recovery, some feedback that we got from the people we interviewed, as well as some opportunities and insights. So as you all know, the primary barrier is cost. Some of these projects require long payback periods. Some materials that are required to reuse the waste streams are costly. And then obviously you have economies of scale that plays a factor. You know, in the 12 projects we selected, these were all very large projects. And so, you know, they were on the larger side, which from our findings, you know, the larger the project, you know, although harder to get approval on because of the capital cost, they have shorter payback periods. It may not be the case for some of the smaller projects, and that's something that we're going to start looking into. But it is becoming more cost effective in general. And so we are seeing more waste heat projects come in the population of projects that we review. Time and risk and status quo is also critical. And a barrier. You know, facility staff are generally very focused on keeping production running and moving forward. And you know, they have their hands full, very busy during the production cycles. And so sometimes it's hard to shift focus to looking for opportunities to reduce waste or energy. You know, there is a risk as well. You know, reusing some of these waste streams could potentially affect the quality of the products, and also, you know, may require some downtime to be able to implement some of this. And so there is some risk there. And then, you know, obviously status quo, if things are running well, you know, there's sometimes a hesitancy to change. And so that also impacts some of the barriers. And I would just add also, you know, on the management side, you know, especially when payback periods are a bit longer, it's sometimes difficult to get approval to implement some of these projects. From a materials and chemical composition standpoint, you know, as Evan mentioned earlier, lower temperature streams can cause corrosion in piping, and so it requires more expensive material to be able to transfer that heat. You know, there is some stress on the equipment. With heat flow in some industrial processes can create mechanical and chemical stress on the equipment. And then heat transfer rates, small temperature differences between heat sources and heat sink lead to reduced heat transfers and require larger surface areas. And finally, transportation and inaccessibility. It's sometimes inaccessible, the equipment there's not enough space to be able to recover this heat, and sometimes moving these waste streams to other parts of the facilities requires additional pumping capacity, or you know, may not be feasible due to temperature drops and things like that. So those are the barriers. Now for insights, there was overarching agreement from the people we spoke to regarding the opportunities for waste heat recovery. I think every industrial facility we spoke to acknowledged that there is tremendous opportunity, and that it's something that is a priority for them, and you know, moving forward, would be looking into. You know, the main drivers are mixed, several factors depending on who you talk to. You know, cost is always at the top, but there's also some process improvements, product quality improvements, safety, regulatory requirements, social responsibility, and GHG, greenhouse gas emission reductions are playing a critical role as well now in decision making, as well as reduction in maintenance costs. So all of these drivers, sometimes a few of them, sometimes it's just one driver, but all of these are playing a critical role. Utility programs and incentives are playing an important role in helping facilities, encouraging them to upgrade their systems and reduce waste. You know, knowledgeable personnel, whether it's the facility engineers on site, or you know, external consultants or energy advisors, have all played a critical role and continue to do so in encouraging projects to be implemented. And as I mentioned earlier, awareness of and importance of GHG reductions is playing more of an important role every day. You know, facilities want to reduce greenhouse gas emissions. You know, it's becoming more, you know, more awareness at the management level as well, which is helping to approve a lot of these projects and move them forward. So we are seeing movement there. Educational resources are helping to increase awareness of the opportunities. So because of, you know, and then energy efficiency programs are providing experienced staff that support facilities. And then finally, on the conclusion side, you know, as I mentioned, waste heat, based on the 12 projects that we reviewed, waste heat recovery is a cost-effective way to reduce energy consumption and CO2 emissions. As I mentioned, the benefits fall into two main categories, cost and environmental benefits. You know, the DOE, in my first slide, I talked about how 20 to 50% of energy input is lost through heat. So there is a tremendous opportunity there across the board to reduce wasted heat. And then, the 12 largest projects showed significant opportunity with payback periods of less than 2 years, and in some cases a couple of months. So there is opportunity there. There are still barriers, as I mentioned in a few slides ago, but we are seeing tremendous opportunities, and we're seeing a lot of excitement in this area. We're seeing a lot more projects come through in this area, especially on the larger side. It was a bit eye-opening this year. We kept seeing across many states when reviewing their energy efficiency portfolios, large waste heat projects. So it was very interesting there. And finally, from a lifetime savings metric, on average, the 12 projects saved 65,700 metric tons of CO2. On a dollar per ton CO2 saved, that was 9.22. Lifetime Therm average was 5 cents. And using average gas price of the 50 states at $5.66 per MMBTU, a payback period of 1.31, which is generally very acceptable in industry. Okay, thank you very much for your time and for this opportunity. If you have any questions, feel free to email Evan or I. Thank you, ACEEE, and thanks, Sharon.
Thank you. I'd like to just thank all of our speakers for very interesting presentations. I think we've all learned some things that we can take home and apply. I would encourage each of you to reach out to the speakers if you have questions or want to have follow-up discussion. Their emails were available, as well as their contact information through the app that we're using with the conference. So thank you, and I hope you have a great rest of the conference.